Finally, let us turn to the examination of correlations between Galaxian properties or scaling relations, which in my opinion is probably the most important and most interesting part of this whole thing. This is what is really telling us of something about formation of galaxies and why they are the way they are. We call them scaling laws because they're power laws that galaxies can be scaled as power of something, like luminosity is proportional to some power of velocity dispersion, for example. And the importance of these correlations is that they are telling us something about how galaxies form, what is the physics behind it. In some cases, if there are correlations between distance-dependent and distance-independent quantities, they're used as distance indicator relations, like Tally-Fisher or fundamental plane. And this is a quantitative way of distinguishing physically distinct families of galaxies, as opposed to something like the superficial appearance in images taken at a particular wavelength. These are physical properties and they differ. You saw this in the last module, like for dwarf ellipticals, which are not ellipticals, and real ellipticals. So a classic example of this type of relation is the Tally-Fisher relation between circular speed of galactic disks and the total luminosity of a galaxy. And it goes roughly as luminosity goes as a fourth power of the circular speed. The power differs a little bit and depending on the wavelength and so on, but that's roughly what it is. And we can measure circular speed either optically through, say, spectra along the major axis of the galaxy or through neutral hydrogen. Even if you just take the whole galaxy into one spectrum, the broadening of H1 21 centimeter line tells you what is the amplitude of the circular speed. Note that in order to get the intercept of this relation correct, you have to know the distances. But to get slope, you don't need to do this. You need to just know the relative distances. And interesting thing about Tally-Fisher relation is that it's a very good one. Its intrinsic scatter is maybe 10%, maybe even less in some cases. This is what it looks like in 5 different filters: blue, visual, red, and very near infrared and near infrared. And you can notice an interesting trend. The further red you go, the better correlation you see. The scatter is smaller. You can understand this because blue light is susceptible both to extras from regions of young star formation, which are unusually bright, and decreases due to the galactic extinction. Blue light is more sensitive to the galactic dust, whereas in infrared, you bypass much of these two problems. So you can think of the infrared Tally-Fisher relation as being the more indicative of intrinsic one. The slope also changes, and that's a slightly different story. And the reason why this is so interesting is that circular speed is basically a property of the dark halo, and luminosity is a product of the integrated stellar evolution in the galaxy over Hubble time. So somehow, dark halo mass seems to regulate star formation history of a galaxy. That in itself is interesting, but even more interesting is the small scatter, because we can think of any number of reasons why the scatter can increase by changing ratios of dark matter to luminous one, by tweaking up star formation differently in different environments, by different kinds of merging and so on. Yet somehow, in the end, we end up with what's almost a perfect correlation. This has been probed in many different ways. You may recall that there is this whole family of low surface brightness disks, which do have normal amounts of dark matter and gas, but just not very many stars. And so even they follow Tally-Fisher relation, which is saying this is not so much relation between starlight and property of dark halo, but between a total baryonic mass and the dark halo. And now that begins to make a little more sense. An equivalent relation for elliptical galaxies is called Faber-Jackson relation, because rotational speeds are not important in ellipticals by and large. Velocity dispersion is, that's where kinetic energy is. Similar thing applies, that luminosity is proportional to roughly the fourth power of the velocity dispersion, here playing the role of the circular speed for the disks. It's a pretty good correlation, but it has large scatter, which cannot be explained by the measurement errors alone. There was something that was causing that scatter, so-called second parameter, and now we know what that is. The other ingredient for elliptical galaxies is so-called Cormedy relation, which relates the effective radii of galaxies with their mean surface brightness. It goes in the sense of mean surface brightness being smaller for the larger, therefore also more luminous ellipticals. This is reflected also in the fact that the more luminous, larger ones tend to have more diffuse surface brightness profiles. This too is a pretty good correlation, roughly goes a slope to minus 0.8, but it's not a perfect one. It too has a scatter that's larger than what measurement errors suggest, again implying there is a second parameter involved. But let's just play with Cormedy relation for a moment to illustrate how you can use these correlations to glean something about galaxy formation. A simple virial theorem argument is that mass will be proportional to the radius and velocity dispersion squared. Now, if we assume that mass to light ratios are roughly constant, which is not such a bad assumption after all, then you can use luminosity as a proxy for the mass. And therefore you can use projected mass density instead of surface brightness. So if you form ellipticals through dissipation, less merging, just pure gravity, no cooling, nothing like that, then kinetic energy per unit mass remains constant. Kinetic energy per unit mass is directly proportional to the velocity dispersion squared. And now going back to the relation between velocity dispersion, mass, and radius, we infer that radius should be proportional to the surface brightness, projected mass distribution, if you will, to the -1 power, which is too steep relative to observations. Now, assume instead that ellipticals form entirely through dissipative collapse. There is no extra stuff being added in, galaxy just shrinks. And because the mass is conserved in this time, a radius goes down, surface brightness has to go up by a square, and so radius will be inversely proportional to square root of surface brightness, which is now too shallow for Cormedy relation. So it's in between. And that suggests that both dissipative collapse and dissipationless merging play a role in formation of elliptical galaxies, and that's almost certainly true. Now, the resolution of the second parameter problem was discovery of the so-called fundamental plane, a family of correlations for elliptical galaxies that unify any number of their properties into two-dimensional scaling relations, often expressed as between radius, velocity dispersion, and surface brightness, but you can use luminosity in place of radius as well. And so here are the four different projections, the Cormedy relation, in the upper left, and you see the little arrow bar symbol in the corner, and that tells you what the errors are, so clearly there is extra scatter involved. The Faber-Jackson relation on the right, top right. The plot of velocity dispersion, which is like kinetic temperature of stars, versus surface brightness, which is like projected density, in the lower left, which is same coordinates as the cooling diagram for galaxies. And there we see absolutely no correlation whatsoever. Naively, you might expect that galaxies with higher kinetic temperatures would also need to have higher densities, but that's simply not the case. This set of plots immediately tells you that there are at least two independent coordinates here, which is why there is no correlation in the bottom left. But since there is some correlation, chances are that this is a flattened distribution in multidimensional space, and indeed, if you combine quantities in such a way to look at this new two-dimensional correlation edge-on, it looks essentially perfect within measurement errors. That is the fundamental plane. It is plane because there are two independent variables, and it's fundamental because it connects fundamental properties of ellipticals. Well, can we understand where these correlations come from? Yeah, up to some point. So we can always start with the virial theorem that always has to apply. And we can then substitute mass for luminosity using mass to light ratios. Now here is the crucial part. If all galaxies were homologous, had just same kind of structure, only scaled versions of each other, then we can relate the important three-dimensional values of, say, mean radius and mean kinetic energy per unit mass to the observed ones through some constant of proportionality, k. And we can account for density structure again with some proportionality constant because we just assume they all have the same shape. Then we can simply, from Virial theorem, come up with the expression that radius should scale as measure of velocity to the second power, that could be velocity dispersion, surface brightness of -1 power, and mass to light ratio to the -1 power. Likewise, we can deduce that luminosity will scale as a fourth power of velocity, or velocity dispersion, just like in Talley-Fisher or Faber-Jackson, -1 power of surface brightness, and -2nd power of mass to light ratio. So you can see that in Talley-Fisher relation, this suggests that surface brightness and mass to light ratio somehow together play the role of the second parameter. For Faber-Jackson relation, the same. For Komety relation, says it's velocity dispersion and mass to light ratios that play the role of second parameter. So this is what Virial theorem plus homology imply. Any deviations of observed correlations from these are telling you something about our assumptions. One of them or another is wrong. We will talk more about this in the next module.